Good evening, my dear students and parents for watching this program. My teacher, today's live session of the biggest classroom of the UAE. I welcome you all for today's live class on nuclear energy and reactor, which would be useful for grade 12 students. In fact, it's a general topic as well. So whoever is interested in studying physics would definitely be, or even otherwise also. It's a general information or general concept, but which is basically specifically required for grade 12 students, those who are doing nuclear energy towards the last phase of the syllabus. So nowadays we all are in an energy crisis. We need energy for our day-to-day uses, and basically all different devices work on one or the other form of energy. So as the population is increasing, energy consumption also is increasing. So we are leading to energy crisis day by day. So definitely we will all look for newer and newer sources of energy to compensate for this. As like when we take the case of India, we have a big population, so very large consumption, rate of consumption of energy is what is there in India. So we are always in need of more and more sources of energy. Basically that's the reason why we have nuclear power plants, we have hydroelectric power plants, we have thermal power plants, all the different types of, 3 types of power plants we have in India. And as far as this country UAE is concerned, they will be commissioning or already commissioned a nuclear power plant in Barak in Abu Dhabi, which is going to be functional in a couple of years. So let's hope the entire world, the world which is facing energy crisis, will get answer by developing more and more resources of energy. Today we are talking about the release of energy from a nucleus, nuclear energy. But of course, a basic process called nuclear fission is what actually invention of nuclear fission. In fact, that's what exactly changed the entire scenario of energy production. So we have got a method to produce energy to a large scale after the introduction of or invention of nuclear fission, for which only the Nobel Prize was awarded. But unfortunately, this is being initially used for the destructive purpose. This is what you can make out from this. You please watch this video before we proceed to the nuclear energy and concepts related to that. Watch this video, please.
At 5:30 a.m., July 16th, 1945, the world entered the atomic age with an intense flash, a sudden wave of heat, followed by a tremendous shock wave. The ball of fire extended 40,000 feet. The bomb packed a punch equivalent to 20,000 tons of TNT, the high end of most of the scientists' predictions, completely vaporizing the steel tower and heating the desert sand into glass for a radius of 800 yards.
So you can make out from the pictures and from the video how big was the destruction caused by an atom bomb which was showered on, which were exploded in Hiroshima and Nagasaki in 1945. as part of the nuclear wars, World War. But later on, so in fact in 1944, it was the invention, nuclear fission, was given Nobel Prize, but the very next year it was used for the destructive purpose. But of course, we are always whenever technologies are introduced, we all will be happy because we will be exploring to newer and newer things. But when it comes to, and the unwise use of those technologies definitely lead to destruction of the or creating agony in the world. But we thought of creating energy in a constructive purpose, for which we devised a method. But before getting into it, let us see how is this nuclear energy released in nuclear fission process. So for this, first we should think of some basics about the nucleus. Inside the nucleus, we have nucleus is, you can assume nucleus as a treasure of energy. So inside the nucleus, the particles are very, held very close. So inside the nucleus, there are protons and neutrons. See, these protons and neutrons inside the nucleus are held very close to each other. How can you make out? This is a very, an example I will tell you. A picture I will give you to make out how dense the nucleus is. You see the density of the nucleus if you want to calculate. The density is, density is mass by volume. Right, mass you can write, if I am writing mass as mass number, that much AMU, atomic mass unit, is what is the mass of the nucleus. Divided by volume, you can write it as being, considering the nucleus as a sphere, the volume is 4/3 pi r cubed. However, that is 3a divided by 4 times pi r. R is, you can write it as r0 a raised to 1/3 cubed, where a is the mass number. So r a raised to 1/3 cubed is a, but this much AMU. Okay. So when you substitute and solve this value, a will be cancelled 3 times. U, atomic mass unit, you may convert it into kilogram, 1.66 into 10 to the power minus 27, divided by 4 pi into, instead of r0, we may write it as 10 raised to minus 15 cubed. So this many kilogram per meter cubed is considered to be the density of the nucleus. So on solving this, approximately you can make out that it will come around 10 to the power 17 kilogram per meter cubed. See, 10 to the power 17 kilogram per meter cubed. You see how big is the quantity. Usually the density of ordinary substances, it comes to be of the order of how much? That is just 10 to the power 3 of the order of this much kilogram per meter cubed. In an average density material is water. Water has a density 10 to the power 3 or 1000 kilogram per meter cubed. But you see the nuclear density comes to be 10 to the power 17, 10 raised to 17 kilogram per meter cubed. So just imagine the picture or the situation. That is, the atom as a whole, substances are made up of atoms. The atom as a whole has got an average density of 10 to the power 3 kilogram per meter cubed, whereas nucleus alone has got a density of 10 raised to 17 kilogram per meter cubed. See, can you make out what exactly, or what you can make out exactly from these figures? So from these figures we can surely make out that the entire matter of the atom is at the center of the atom, that is the nucleus. Okay, so that is, the whole mass is squeezed into the nucleus. That is the reason why the density is extremely high. So if you compare these two values, that is, density of ordinary substance is 10 to the power 3 and density of density of ordinary substance, that is density of atom, is 10 to the power 3, whereas density of nucleus is 10 to the power 17 kilogram per meter cubed. So this extreme value of density, so basically two major aspects you can make out from this. Number one, the density, see, in between we lost A, A is gone. That is, density of a nucleus is independent of the mass number. Density, all nuclei have the same density. You should know that. There was a question in one of the papers. The mass numbers are given, the ratio of mass numbers given 1 is to 27, I think. Yeah, 1 is to 27. The mass numbers ratio given, you have to find out the, what is the density of the ratio of the densities of the nuclei. Remember, densities of the nuclei independent of mass number, so the answer is 1 is to 1. So one aspect you can make out from this calculation is that the density of the nucleus is independent of the mass number, right? And second thing we can make out from this is the density is, what you say, extremely high density of nucleus indicates that the entire matter of the nucleus or entire matter of the atom is concentrated inside the nucleus. That means the nucleus is held with a very strong energy, very strong force. We call it as nuclear force, which is considered to be the strongest force in nature. The protons and neutrons, between protons and neutrons there is force, between neutrons there is force. Those forces are called nuclear forces. So the nucleus is held together. The extremely high density shows that there is a very, very, very strong nuclear force existing inside the nucleus, which binds the nucleus, binds the nucleons, that is protons and neutrons, inside the nucleus. So there is an energy called binding energy. So there is energy existing inside, that is called binding energy. Okay, so this binding energy is what is present inside the nucleus. Too much of energy it has got. So in case of a nuclear process, there are many nuclear processes. One of the nuclear processes only we are going to study today, right? And similarly we have, that is what is nuclear fission, right? Then similarly we have nuclear fusion, another process. We have again one more, from radioactivity we are getting energy. So for all these kinds of nuclear processes, there is a release of energy. Energy is released from the nucleus. So it's like nucleus is a treasure of energy, too much of energy inside. So from that, under favorable circumstances, energy may be released. This energy, we can call it as nuclear energy. Okay, so what exactly, or where is the energy coming from? That is, from nucleus. We know energy cannot be created as such. It can only be converted from one form to another. That's one concept, But in this situation, we may make use of a concept given by Albert Einstein, which is the famous mass energy relation, E equals mc squared. So this equation indicates that when a nucleus is undergoing a nuclear process, a nuclear reaction, there will be definitely a loss of mass. Some amount of mass would be lost as the result of the reaction. So lost mass, that is what is being converted into energy. So the energy produced from nucleus is basically due to the loss of mass. Okay, so for example, in a reaction, one AMU is lost. One AMU, or one unified mass, it is lost during the reaction. That means it releases some amount of energy. How much amount of energy? Mass, you put it as 1 AMU. 1 AMU is nothing but 1.66 times 10 to the power minus 26, or 27 rather, multiplied by c squared. Okay, instead of c squared, we have 3 times 10 to the power 8 squared, speed of light. Okay, so this many joules of energy would be released whenever energy is, 1 AMU is converted into energy, right? So during a reaction. So if you want to get it in electron volt, what we should further do is divide by 1.6 times 10 to the power minus 19. That much is the amount of energy released during a nuclear reaction, which causes a loss of mass of 1 AMU, right? But this is in electron volt. Instead, if you want to get the energy in million electron volt, you should further divide by 10 raised to 6. So ultimately, you will get around 931.5 million electron volt you will get when 1 AMU is lost in the reaction. So due to loss of 1 AMU, the energy released during a reaction would be this much million electron volt. So this is how energy release happens inside a nucleus, okay, or as a result of a nuclear reaction, okay. So all of you got the picture. That is when 1 AMU is released, sorry, 1 AMU is lost during a nuclear reaction, we get an energy of 931.5 million electron volts. So in that case, I will give you a small or simple example. This is a very useful concept for you to solve some numerical problems which may come in the exam. Say, just generalizing, just imagine there are two nuclei combining, two nuclei A and B, just to understand the concept. C and D, there are two nuclei formed as a result of the nuclear reaction. So A and B are two nuclei. After a nuclear reaction, it is converted into C and D, two other nuclei, plus energy is released. You know, usually energy release is given by the letter Q. That is Q value of the reaction. Energy is released. So our question is, how much Q is there? How much is the energy released? Imagine the masses are given. Let's say A is given to be 3.1 AMU, and B's mass is given to be 5.3 AMU. Okay, and C's mass, let it be say 2.8 AMU, and D's mass, let it be 4.1 AMU. So all the masses are given, let's say, in AMU. Question is, how much is the energy released during the reaction? So the thing is that you can make out clearly how is the energy released now, or how much is the energy released. Let's see. So what will be the mass of the reactants before the reaction happening? Mass is definitely 8.4 AMU. See, 5.3 plus 3.1. That is 8.4 AMU is the mass released. Similarly, this one would be 6.9. 4 plus 4.1 plus 2.8. Okay. So just subtract it. So 8.4 minus 6.9. So how much it is going to be? So it would be, that is 8.4 minus 6.9. So it's going to be 1.5. Correct? So 1.5 AMU is lost during the reaction. I hope it is clear. Okay? It's correct only, no? 8.4 minus 6.9 is equal to 1.5. So now how much is the energy? Therefore, what will be the energy released? Q. The Q will be, that is energy lost, sorry, mass lost is this much. So what will be the energy released? Previously, at the beginning I said, if 1 AMU is lost, 931.5 million electron volts energy is released. So in that case, if 1.5 AMU is lost, how much energy will be released? Just multiply it by 1.5. 1.5 times 931.5 million electron volt. You see, these kind of calculations are really important in numerical problems. You know, this is, I was giving just a simple example to show how the energy calculations can be as far as the nuclear energy release is concerned. Okay, so this will be like a common mistake is, you just remember you know, the equation E is equal to mc squared is what is employed over here. So if the questions of this sort when comes and if masses are given in AMU, sometimes you may use the equation E is equal to mc squared and calculate the energy. But remember, this is the way which you may adopt. Okay, and you know, already we calculated how much energy release may be there when 1 AMU is lost. So just find the mass difference in AMU and multiply by 931.5 million electron volts, straight away it will give you the answer. Okay, I hope it is clear. So now I'll show you the way nuclear fission reaction occurs. First of all, one of the reactions, one of the ways the energy is released during nuclear reactions is nuclear fission. So we are studying this case of nuclear fission. Okay, so the fission bomb is what I showed you at the beginning of this class. Okay, nuclear fission is one of the ways the energy is lost. Sorry, energy is released. You see, nuclear fission means, you know, think of the different types of nuclei from the beginning, like, you know, the lighter nuclei onwards. If you look at, or if you assume, we can make out one thing. As we get into heavy nuclei, such as uranium, in heavy nuclei like uranium, especially the isotope of uranium, uranium-235, inside the nucleus of uranium-235 there occurs a very delicate balance among the forces, you know, delicate balance. Okay, so that means in the nucleus is you know, the case of radioactivity, you know, radioactivity means nucleus will be already unstable, or it will keep on emitting radiations because it is unstable. But in the case of nuclei like that is uranium 238, all right, whereas in the nuclei like uranium 235, what happens is there will be there is a delicate balance among the forces. Okay, so what happens is delicate balance means what? Any disturbance in the situation inside the nucleus will cause or will make it highly unstable. So highly unstable means it would be splitting into two fragments. Okay, so this is what exactly nuclear reaction or nuclear fission is. That is a nucleus such as uranium 235. The uranium 235 is just as an example. Uranium 233 is there, plutonium 239 is there. So for these nuclei, what happens is so inside the nucleus there is a delicate balance existing. So due to which, when you bombard it with a suitable particle, here which is a suitable particle, you know, it is neutron, because neutron can easily get into the nucleus. It is neutral particle. So the neutron when goes inside the nucleus, so nucleus already it was about to be unstable. That's the meaning of saying delicate balance. Okay, so the nucleus is in a delicate balance, due to which a sudden when it will split into two fragments. This is what is exactly happening during nuclear fission reaction. So during nuclear fission reaction, a neutron is used to bombard into the nucleus of fissionable nuclei, such as uranium 235. So such nuclei, what happens is the neutron when goes inside, it will make the nucleus of the nuclei like uranium 235 highly unstable, and soon it will split into two fragments. When it splits into two fragments, what happens is there is a large amount of release of energy due to the difference of mass, due to the loss of mass. That is basically when uranium 235 splits, it will lead to barium and krypton. Along with 2 or 3 neutrons also will be released. You just watch this simulation. I will show you a simulation which will clearly explain what nuclear fission reaction is. Watch this. Okay. See, I'll just pause it. You have seen, I hope you have seen this. Once again, I will do one thing. Once again, I will show you what exactly is happening here. Okay, so you see on the screen, you can see uranium 235. Okay, uranium 235, into which I am going to bombard a neutron. Okay, bombard a neutron into it. You see, carefully you see what all things coming out, which all nuclei are produced as a result of the splitting. You just watch and see. I'll just pause in between. See, now it is highly unstable. Okay, now what happens? It splits. When it splits, it is going into two fragments, which are the barium and krypton nuclei. And you can also see on the screen, you just observe this. These are the neutrons. 1, 2, 3 neutrons you can see. So the neutrons. So you can see over here it is. This is indicating neutron. So okay, just watch once again. I will show you the process once again. Watch it. Okay, a neutron. I am going to bombard a neutron. It is going to split into fragments, right? Fragments, and it is releasing a lot of energy. This reaction is what is called nuclear fission reaction. Now let us think. So this releases energy. Okay, now let us think in this way. What happens if too many nuclei are there? Okay, so that is one neutron is bombarding a nucleus that releases energy, and this energy is what is due to the mass loss or loss in mass, and this is other daughter nuclei are produced. Along with the daughter nuclei, here the example barium and krypton. What happens along with the daughter nuclei? The neutrons also are released. These neutrons may cause fission on other nuclei as well, right? If it causes fission on other nuclei, what will happen? You know, there will be those nuclei will again split. Okay, again it will release more neutrons along with the daughter nuclei. Those neutrons will again cause fission, so there will be a continuous or subsequent nuclear fission processes happening, so which will lead to a release of tremendous amount of energy. This is exactly what is called chain reaction, right? This is what is happening in atom bomb. So in an atom bomb, what is happening is chain reaction. You know, a nuclear fission happens, a neutron splits a nucleus, and that nucleus releases neutrons. Those neutrons are again causing fission, right? That's again, it keeps on continuing. These subsequent fissions happening in a very short span of time will release tremendously high amount of energy, which if as a whole, if it is released, all of a sudden if the energy is released, what will happen? It will lead to big destruction. This is what is exactly happening in the case of atom bombs. So I will show you another simulation which will help you to understand what a chain reaction is. Okay, so I am going to just see, I am increasing the number of nuclei. So I am keeping some nuclei of uranium-235, okay, and see what is happening. Just watch this. Okay, so uranium-235, I am going to bombard it with the neutrons. I will show it again, just see first. So some uranium caused fission, and some neutrons released, and those neutrons further cause fission nuclei. So I am going to increase the number of nuclei. See, now more nuclei are there. Just watch, 50 nuclei I am using. Just to understand the concept, you just observe here what is happening. A neutron, I am going to bombard a nucleus with a neutron. Just closely watch the screen and see what is happening. Okay. Yes. See, this is what is exactly what chain reaction. So you might have watched this simulation which shows one neutron is splitting into two nuclei, one nucleus splitting into two nuclei. Those nuclei release neutrons. Those neutrons are causing more fission. So tremendously large amount of energy is released due to a large number of nuclear fission process continuously happening. So at the beginning of the class, I showed a video of the atomic explosion happened in Hiroshima and Nagasaki, which was basically the result of this uncontrolled chain reaction. So once if it is initiated, you cannot control it. It will keep on developing, and large amount of energy will be released, which will definitely cause a lot of destruction. And a very sad part of it is a lot of harmful radiations also will be emitted out of it. These harmful radiations can even cause genetic mutation. That is, it will be prolonged from generation to generation. So lots of adverse effects will be there due to the exposure to the nuclear. That is the nuclear radiations coming out of these reactions. This is the reason why we have to take extreme care while planting nuclear power plants. Extreme care. Okay, so there are the countries definitely take safety measures in developing nuclear power plant or making nuclear power plant. Lot of lots of energy release is there in the nuclear reactor. It is a it will be a boon to humanity if this much of energy is released in a controlled manner. So when you use energy, when you produce energy in chain reaction in a controlled manner, definitely safety measures are taken. So those safety measures we will discuss, but before that, before going to that, I will show you the chain reaction process once again. You just observe. Now this time I am going to use uranium, instead of uranium-235, let me use uranium-238. Instead of uranium-235, this is uranium-238. So let us see what is happening if it is uranium-238. See, I bombarded it with a neutron. See, nothing happened. So it was the neutron was absorbed inside once again. See, it is absorbed and it is converted to uranium-239 only. So the nucleus was absorbed inside because it is not fissionable. So there are nuclei which are fissionable. So but instead, if I am using uranium-230, so now I am reducing uranium-238 and increasing the number of uranium-235. Then what else you can make out is, see, this is uranium-235. Let me see how it is. See, this leads to fission and leading to continuous chain reaction. Okay, so this is what is happening in chain reaction. I hope the concepts of chain reaction it is clear. Okay. So, now we will see what is the situation when or if the nuclear energy to be harnessed in a controlled way. It is all, obviously it will be a good big boon to humanity, is right? It is a big thing. If at all, this energy release in this pattern is not like once if it is initiated, it will keep on developing like that, and there is no control, and energy will be used, or energy cannot be used for useful purposes. So, we will see now how will you harness this energy for useful purposes, or how will you control this energy. This is what is happening in a nuclear reactor. Okay, so about the nuclear reactor, so nuclear energy release and all we discussed. About nuclear reactor, we will go more details of this after a short break, but remember, this is a live classroom. If you have any confusions on these portions, even not only not necessarily to be restricted to this, anything if you want to know from physics related to grade 12 or even grade 11, you can get back to us, you can call us, and we will clear your doubts. Okay, so now we will join again for discussing nuclear reactor or controlled nuclear reaction after the short break. Okay, stay tuned, we will be back soon.